Routing every agentic workflow through a cloud-based frontier model guarantees a cascading series of hardware and financial bottlenecks. We are taking simple tasks and feeding them into remote server farms that house the sum total of human knowledge. The first immediate liability is security. Sending any prompt to a remote server introduces the inherent risk of interception, exposure, or third-party retention. Sensitive business data leaves your localized environment and sits in a black box you do not control. Then the token economics break down. Multi-step reasoning loops consume tokens exponentially faster than API prices are dropping. Running multiple layers of inference through an agentic framework ensures that even seemingly cheap models compound into massive operational costs over time. But the strictest ceiling on cloud inference is human psychology. Research on artificial intelligence interactions reveals a rigid threshold for believability. Humans perceive any response delay over 4 seconds as a broken or disconnected experience. A standard API round trip to a large model routinely violates this 4-second limit. The data must travel over a network, wait in a compute queue, generate a massive response, and travel back. Relying on remote infrastructure for real-time user experiences guarantees a slow, expensive, and fragile application. Offloading these tasks to on-device small language models, or SLMs, eliminates network latency entirely. When engineered correctly, pushing inference to the edge actually increases reliability. This chart shows the final results of a complex JSON summarization task. The local 3 billion parameter Llama 3.2 model perfectly matched the structural validity of the massive Claude Sonnet model, while driving the median response time under 1.5 seconds. Achieving a 100% valid, structurally complex JSON output from a model thousands of times smaller than a frontier LLM immediately invites technical skepticism. Measured, precise, this level of local performance stems from a specific engineering methodology called prototype big, deploy small. Extracting frontier-level reliability from limited parameter models requires a systematic reverse engineering of the task itself. We have to map out exactly how an SLM processes data differently than a massive LLM and build a pipeline that leverages those precise constraints. The process begins by proving the feature is computationally possible. You prototype the logic using the largest, most capable foundation model available. This initial step clarifies the actual compute requirement. If the task relies solely on visual recognition or transcribing audio, you route the data to dedicated vision or audio models. You only incur the overhead of an SLM if the task explicitly demands generative text and reasoning. Once the foundation model confirms the generative text logic works, you freeze its successful outputs. This diagram illustrates 14 raw social media conversation threads run through a frontier model to generate both short summaries and heavily annotated summaries. This extraction forms a golden dataset of 28 curated input-output pairs. This dataset serves as the immutable baseline for all downward scaling. To shrink the model, we measure smaller candidates against 4 specific evaluation gates: simple JSON parsing validity, length compliance, response latency, and factual consistency. Testing whether a model outputs parsable JSON is a straightforward binary check. Scoring subjective factual consistency requires weighting the model's summarization accuracy against aggressive hardware and latency constraints. Scaling down without this mathematical ground truth is blind guesswork. You must define success rigidly before attaching a smaller parameter count. With the baseline set, we run a capability evaluation. We quantitatively test a roster of small, local models against the exact same dataset to see how they stack up against the frontier giant. Consumer hardware dictates the rules of engagement here. 1 billion parameters requires roughly 2 gigabytes of RAM in FP16 quantization. The model must physically fit within the memory limits of a standard smartphone. This scatterplot maps the performance space. Claude Sonnet establishes the baseline in the top right quadrant. Highly accurate, but dangerously slow for real-time mobile interactions. Blindly selecting an industry-favorite SLM like the 5 billion parameter Gemma 4 yields moderate accuracy but unacceptable latency, pushing response times out to 8 seconds. Over-optimizing for speed produces the opposite failure. The 1.5 billion parameter Qwen 2.5 returns answers in 1 second, but its factual accuracy drops well below acceptable limits. The optimal target is the SAGE model, small and good enough. The 3 billion parameter Llama 3.2 hits the necessary equilibrium, maintaining 90. Applying explicit negative constraints, telling the model exactly what it cannot do through strict rules prompting, causes an immediate drop in accuracy. Small models struggle to weigh and follow negative literal commands compared to positive examples. Forcing the model to reason through chain-of-thought logic yields a slight improvement in factual accuracy, but imposes a massive 600 millisecond latency penalty. It burns too many compute cycles thinking out loud. Few-shot prompting provides the mathematically optimal solution. Feeding the SLM a few concrete examples of the desired input and output spikes the accuracy to near maximum levels, while only costing 200 milliseconds in processing time. Small language models excel at rapid pattern matching. They absorb formatting and structural intent from examples much faster than they can deconstruct abstract rules. Optimizing an SLM requires aligning your prompting with their inherent processing style. You achieve higher accuracy by feeding the model's pattern-matching strengths. Even with perfectly tuned few-shot prompting, a restricted parameter model will eventually hallucinate an error count or overshoot a strict character limit. The final architectural step removes these responsibilities entirely. You route the raw text output from the SLM through deterministic application code, standard logic filters designed to truncate string lengths and validate reference counts. Never waste expensive inference cycles asking a generative model to perform basic math or structural validation. Offloading those specific checks to standard application code instantly secures 100% JSON structural validity and length compliance. The lingering fraction of a percent in factual discrepancy disappears upon manual review. It is an artifact of the evaluation framework, where the massive foundation model acting as the judge strictly favors its own verbose phrasing over the SLM's concise output. Reliability in local AI is achieved by aggressively narrowing the model's operational responsibilities. This engineered pipeline operates entirely within the native boundaries of the user's hardware. The input, inference, and post-processing all loop securely on the device itself. Moving the workload to the edge drops API costs to zero. It eliminates network round trips to hit sub-2-second latency targets and guarantees that sensitive data never touches an external server. Sustaining this performance requires treating prompt updates and model swaps with the exact same rigor as pushing production code. You must run automated regression evaluations in a CI/CD pipeline to monitor the outputs. Without automated oversight, a slight tweak to a prompt can cause a stable SLM to hallucinate references or output massive paragraphs, instantly shattering the workflow. Protecting the user experience demands continuous mathematical testing against your golden dataset. Look at the tasks currently routed to massive foundation models in your own inference pipelines. Measure the cost, the latency, and the compute requirements against the actual objective. You can drastically reduce friction by utilizing models that already ship natively within user environments, like Gemini Nano operating directly inside the Chrome browser. Paying frontier cloud costs for simple deterministic logic is an architectural flaw. When you prototype big and deploy small, you can deliver frontier-level performance right at the edge.